That's you.
Thank you very much. Hi, everyone, and welcome. It's a pleasure to be here and present on the Scenes GPU Day again. And thanks for introducing my topic, which I'm going to talk about today. So I would like to start with a very brief introduction that I always tell at the beginning of these types of topics. So as you all know, unfortunately, cancer is still one of the leading reasons for death today. And our aim is to treat it as efficiently as possible. Now, how can we treat cancer? So first of all, we can use surgery. Is it better? Hopefully. So we can use surgery, chemotherapy. Also an emerging method is immunotherapy. But what I'm going to talk about today and what's the most interesting for us today is radiotherapy. So radiotherapy uses the ionization of particles to destroy the DNA of cancerous cells. And most of the time, or at least this is the most widespread method nowadays, we use photons for radiotherapy, but also a very, very emerging method is hadron therapy when we use protons or heavier ions such as helium or carbon ions. And the question is, why are hadrons so amazing when it comes to treating cancer? And the reason you can see on this plot is the so-called Bragg peak. So what you see here is how these particles deposit their energy when they enter a medium. So at the beginning, they deposit little to no energy, and then they will have a sudden peak of energy deposit. This is called the Bragg peak. And this basically, if you imagine that we shoot a particle through a cancerous tumor, we can fine-tune the position of this Bragg peak, so the maximum energy deposit, in such a way that it will be exactly in the tumor, and this will spare the surrounding healthy tissues from a lot of those deposits. This, for example, is not true for the photons. And in order to be able to tell where we have to put exactly this Bragg peak, we have to do a very precise imaging before the treatment. And here comes the problem, because nowadays, in the clinical routine, we do the imaging with photon CT, X-ray CT. And the problem is that photons see the world entirely differently than hadrons. So what we use to express how the protons absorb, how the photons get absorbed in a tissue is so-called Hounsfield units. But what we want to know is the so-called RSP, relative stopping power units, which explain how much the certain hadrons slow down in the materials compared to water. And we have some lookup tables we can do this so-called conversion, Hounsfield units to relative stopping power units, but this conversion will bring us about 7% uncertainty. And this is already a lot if you think about that we want to do very, very precise treatment planning. So what could be the solution? Well, let's do the imaging with the particle that we will use for the treatment as well. Use the same particle for imaging by simply choosing a higher initial energy for the imaging than what we would choose for the treatment. So the Bragg peak will not be inside the patient, but right after the patient in a detector. And before I talk about the detector and the concrete imaging techniques, I would like to compare protons and heavier ions a bit. Just a bit of a disclaimer. Most of the time, we mean the heavy ions that are actually heavy, but in medical physics jargon, this is actually light ions, the helium and carbon ions, for example. But since my talk is basically comparing these electrons for imaging, let's compare them. So as you can see, the Bragg peak is getting narrower and narrower as we're going towards heavier ions, which means a more precise treatment. However, heavier ion therapy, so like helium and carbon ion therapy, is a bit less widespread than proton therapy, because proton therapy is a bit cheaper and easier to carry out. But it is an emerging method, so yes, it would be useful to check if it's worth doing imaging before heavy ion therapies with these heavy ions, so helium and carbon ions, because we would have the advantage of using the same instrument that we would use later on for the treatment, so we wouldn't need to move the patient, for example. But in order to see if it's feasible, we need to check some parameters. One of these is the accuracy of imaging, so how accurate we can reconstruct objects with these ions. And the other very crucial parameter is the dose deposit of particles. So I mentioned the detector, and I want to say a few words about the Bergam proton-CT collaboration. That is that our group is part of the Bergam proton-CT collaboration, our Wigner research group. And the goal of this collaboration is to build and utilize a proton CT that is based on the high energy particle detectors that the heavy ion experiment of CERN LA uses as well. The base of the detectors is this so-called LPI chip, which stands for Alice Pixel Detector. And this is a monolithic active pixel sensor, a very, very advanced technology. And the reason it's very advanced is that the sensors and the readout electronics are on the same layer, making it extremely low material budget, which is very useful for high energy physics and also for proton CT. So this is an extremely small chip, 3 times 1.5 centimeters squared with 1024 times 512 pixels, extremely small pixels. And we have 108 of these pixels in one layer of the detector. And this is the detector we would be using in the proton CT. This is a high granularity digital tracking calorimeter, which means it has tracking layers and calorimeter layers as well, making it possible to measure positions and energies extremely precisely. And this is exactly what we need for imaging. But the question is, how do we get from the particles to the image? So first of all, we have to irradiate the phantom or the patient with high energy hadrons. High energy here means the magnitude of 100 megaelectron high energy that we talk about when we talk about high energy. But in this case, it means this. The second step is the aforementioned detector system that senses the signals. And I have to add it here that currently we are using Monte Carlo simulations for this step. And this, for this, we needed to utilize a CPU. And I'm also going to talk about these details on the next slide. But first of all, what is the third step? So we have the signals and we have to process these signals, which essentially means reconstructing trajectories and predicting energies. And once we have the energies and the positions, we can go on to the image reconstruction. And this is actually the part I am also working on. Image reconstruction means to get the so-called relative stopping power map of the irradiated object. This you can imagine as a sort of density map. And for this step, I will also talk about it in details. We also use a lot of GPU. So I promise that I will talk about the simulations. So the reason why we have to do simulations in the first 2 steps is that we don't have real data yet from the real detector. Hopefully we will at some point. But right now we are using GN4 and gate simulations. And for that, basically the simulations look like the following. So we shoot the imaginary particles through the imaginary or like simulated phantom. And this phantom is the so-called CTP404. This is an epoxy cylinder that contains little rods of different materials. And it is used for measuring relative stopping power reconstruction accuracy. And the way we actually did these simulations is we scanned through this phantom. What this means is we were rotating the phantom. This very happy emoji is the phantom right now. So we were rotating it and scanning it in every angle, and also scanning through this axis for 155 millimeters in every millimeter. And scanning means that in every angle, in every degree and every millimeter, we shot 1,000 primary particles through the phantom. If you do a quick math, this is a bit more than 55 million particles, actually, which is a lot. The initial energies of the particles were 200 30 MeV per unit for protons and helium ions, and 430 MeV per unit for carbon ions. And I have to edit here that especially in the case already for protons, but especially for heavier ions, it is a very, very time-consuming simulation, especially if we do it so precisely with so many turns and scans. It is extremely time-consuming, so we used GPUs here massively in the Wigner Scientific Computational Laboratory. And another disclaimer that this is only, if you imagine, this is only in 2 dimensions. So we only checked one slice of this cylinder, but since it's cylindrically symmetrical, it doesn't really matter which slice we're checking. And now I would like to continue with the image reconstruction techniques. There are 2 main reconstruction techniques which I would like to mention. The first one is called integral transformations. These are the Redden and inverse Redden transformations. Here you can see this is basically how it looks like after the imaging, and then we can transform this so-called sinogram back to the to get the original picture, how it looks like originally. And this is a very straightforward technique, but unfortunately it is based on the fact that particles travel through the object without scattering at all. And this is unfortunately not true for hadron, so we can't use this for hadron CT. But instead, we have the other main reconstruction technique that is called iterative techniques, which model the problem as a linear equation system. Such a linear equation system you can see here. It's a very simple one. A is a matrix. It contains the so-called interaction coefficients between the particles and the pixels, which basically means how much a particle contributed in one of the pixels. X is the vector that we're interested in. This is what we want to calculate. This is the estimated particle relative stopping power values. This is what we will get this map on, which we can convert to the grayscale image. And Y is the vector that contains the known so-called water equivalent path length values of the particles. So how does an iteration look like? So we have an initial picture without any sort of structure. It's quite blurry, and we do some corrections on it. So we will do a bit more iterations. We will use a bit more particles for trying to make it look a bit better. And what you see here is an absolute difference plot. This is basically the absolute difference between the so-called ground truth image and the current state, current phase of the reconstruction. And if you saw nothing here, it would mean a perfect reconstruction, because white means 0 difference. This is what we want to achieve, but unfortunately that's probably impossible. But as you can see, as we're processing forward, the reconstruction is getting better and better. There are many, many iterative techniques, such as the algebraic reconstruction technique, the art and its children, the parallel art and the simultaneous art. There is also the diagonally relaxed orthogonal projection, the drop, but I'm not going to talk about this. I wanted to mention so you see that we have these as well, but what we are working on is the so-called Richardson-Lucy iteration. So this is a somewhat novel model that's used for medical physics, novel in a sense never been used before for medical physics, but originally it was used quite early already in optics and astronomy for Poisson distributed measurements. And the math is very beautiful behind it. We actually see this somewhat ugly formula, but this is basically the solution to this linear equation system. And while it's very beautiful mathematically, it's very, very challenging technically, because as I showed you before, we are talking about millions of particle trajectories. So it is very, very computationally demanding. So here we also utilized GPU massively. What this part is basically is a C++ code that we sped up with CUDA. And what it does basically execute the iteration cycle, this iteration cycle in the GPU kernels. For this, we also utilize the Wigner Scientific Computational Laboratory. And we use these NVIDIA GTX cards, which you would, if you are familiar with these, which you probably are, you would say, okay, but not the highest technology available on the market today. Yes, and this is exactly what we wanted to show, that we don't need supercomputers to run a reconstruction like this, because unfortunately we also don't have supercomputers in hospitals. So naturally we need a bit less advanced technology. So yes, exactly. And our goal was to maximize resolution with this reconstruction while minimizing runtime as much as possible. If we have a reconstruction algorithm, which we have to evaluate it somehow, how good it works. And I would like to talk about a special type of evaluation. We could also evaluate, for example, the spatial resolution, but in this, in the scope of this research, we only checked the relative stopping power reconstruction accuracy. And the way we did that is that we have this so-called ground truth image, which has perfect contrast, zero noise, zero blurring. So it's essentially a perfect image with the publicly available RSP values of these inserts. And what we do is determine the center position of each insert. And then on the reconstructed image, find the exact positions and calculate the mean relative stopping power in these positions and compare them with the ground truth values. And now I would want to talk about our results, because this is what the most interesting part is. So you see a lot of plots on this slide, and I'm going to explain all of them. So we can go strategically through the particle types, so the beam types. The first, so here you see the, I don't know if it works, but there you see the aforementioned absolute difference plots, these red-blue plots. And the first row from this is the protons. And here you see the zoomed picture of each insert of the phantom. So here we have the protons, the helium ions, and the carbon ions as well. And the way we can check them is, for example, if you compare the last phase of the protons, you can see that it's much worse than, for example, for the carbons. But we can go through the plot in a way that we check the number of particles we used for the reconstruction. So here in the first column, we have 20,000 used particles, then 1 million particles, and then at the end, 25 million particles. This is the final picture. This is the maximum accuracy we can reach with the reconstruction. And here you also see this diagram, which basically shows us for each type of material, except for the air, the relative difference between the ground truth RSP values and the reconstructed RSP values. And in the legend, you see the mean absolute difference between the ground truth and the reconstructed values using 25 million particles. As you can see, the protons already showed quite nice results. So they already performed quite well with 1.2% relative difference. But as you can see, the carbons were extremely outstanding with the maximum of 0.6% mean absolute error, which was very, very nice to see. And the heliums were somewhere in between. And another thing that we found crucial is the dosimetric performance. So we have seen already that the imaging is feasible with the helium and the carbon ions. So it is really worth checking how much dose this means, because this is essentially the most crucial part to talk about human patients, how much dose they have to suffer. And for this part, we have to take two things into account. The first thing you see on this plot is the convergence of the reconstruction accuracy. So what we have seen is essentially that we might not need 25 million particle trajectories in order to reach this final reconstruction accuracy. As you can see, the reconstruction accuracy starts to converge much sooner than the 25 million particles. So here we basically set some thresholds, how many particle trajectories we have to use in order to reach the final reconstruction accuracy. And the other thing we had to take into account is that, as I mentioned, and that's why it was a disclaimer, we only reconstructed a two-dimensional slice of this cylinder, and the human head is definitely three-dimensional and definitely not cylindrically symmetric. So in the human head, we had to extrapolate our results to calculate with the volume of the human head, with the density of the human head, and making it three-dimensional. So multiplying it with the number of slices we would have. Still, taking these things into account, we have come to the estimation that even for carbon ions who have a much different physics than, because they will suffer much more nuclear scattering, there will be much more secondary particles. Even in their case, the doses are less than in the case of a typical X-ray CT for a human head, which is around 40 milligrays. And for carbon ions, which had the most, it was still only 22.7 milligrays. And with that, I would like to come to the summary of my talk. So we have compared CT imaging with different particles used in hadron therapies, and this talk was probably a bit of an outlier in all the programming and GPU and quantum computing, but I really want to stress the fact that if we didn't have the available GPUs in the Wigner Scientific Computational Lab, we wouldn't have been able to do this and come to these nice results. So yes, I would like to say thank you again for that. And I also want to say, in just the coffee break, I submitted it to the archive, so it will soon be available. Unfortunately, I don't have the number of it yet, but hopefully tomorrow. So yes, we used a novel but already did image reconstruction method with the Richardson algorithm, and so that a good relative stopping power reconstruction accuracy is possible, and it was especially outstanding for carbon ions, for example. And we have also seen that the deposited dose is, it was only an estimation, but still it looks like it is negligible for protons, and even less in the case of carbon ions than the standard X-ray CT. So to conclude, it could be worth utilizing the heavy ions for imaging, but naturally, there's no such thing that the work is done. So we have a few future plans, such as more extensive testing using three-dimensional phantoms, hat phantoms, and so on. And with that, I would like to thank you very much for your kind attention.
So is there any question?
Very nice talk. I've just noticed on the figures that, interestingly, on the carbon case, the resolution maybe not that good. So the very small features, it may look better on the proton. I am not sure if it is true. And on the, at least on the carbon, you see the small dots more clearly, while we cannot see it on the, so it may just be just an optical illusion. But yeah.
Yes, that's true. And yes, I think in general, it is true that with the carbons, we reach a better resolution. So these tiny structures will be a bit more present or a bit more outstanding. But it's actually quite interesting to see that you don't see that big of a difference when we use not so many particles. And the more particles we use, the more outstanding this difference is between the different beam types. So yes, I think, yes, it's entirely true that these small structures will be much more visible. And I think that's also why they are outstanding as an imaging source or imaging particle.
Thank you. It's very nice talk. I was wondering during the talk that if we would go for more higher heavy ions, then we know very well that the Bragg peak getting more and more narrow. So practically you have a more sharper, more sensor things. But maybe there's a limitation with that. So if technologically it would be possible easily to choose a higher, heavier ion, that do you see any point that the whole method can have a limitation because it's the observational way, or the resolution is too fine to get something more properly? This is a bit related to what Pishti is saying.
Yeah.
So,
Yes, I definitely think there would be some limitation, and especially because, for example, I think when we do imaging, we want to reach a resolution that's so. For example, in a case of RST reconstruction, we can reach a finite resolution, so it can't go to infinity in that sense. But I don't really know. I don't know exactly where this limitation would be, for example. So what would be the best possible that we can reach, and what kind of particle? Because it's not a limitation of resolution, but a limitation of technology, for example, that while we could use, I think in theory, heavier ions, even heavier ions, I don't know if they are that easy to use technologically or technology-wise. It's already, I don't know if I've mentioned that, but you know for sure that carbon and helium therapy, for example, it's less widespread because it's more expensive, and the instruments and the tools are just way more expensive, and I think, or at least that would be my educated guess, that as we're going towards bigger and bigger and heavier particles, the more difficult this becomes. So I'm not sure it would be worth it, because I don't know if we would reach that big of a difference in the resolution.
So I was wondering that this could be an interesting point to investigate a bit, because if you think that tenth of a millimeter is about the size of the edge of the scalpel, so if you go beyond this, then you have a much more precise tool to kill things or cut things. But if it's a good question at whether we have to go or not.
Yes, absolutely. And actually, as long as we are working with simulations, which we are right now, it is in theory possible that we use whatever ion we want in Gen4 and gate. It will probably take a long time, but that's why we have the GPUs. So yeah.
So one more question, that actually you are solving a much harder problem that you should be. So you solve for a fully general shape, like dots or mass distribution can be any. And actually for these phantoms, this is not the case, because you have just these spots or whatever. And I guess that for a real brain or whatever body part, it has some typical shape, or actually the dimensionality or the complexity is much lower than the raw pixel space. So are there directions how to handle this and make this lead to better resolution with even lower radiation?
Yes, absolutely. That's a good point. And I think Bente, the next speaker, will actually talk about this. Yes, and I don't want to spoiler anything. So yes, I think it will be included in his talk.
I'm looking around. Is there any other questions maybe for one?
Maybe a little bit provocative question, but bear with me. So I'm also dealing with computer vision in general, and one of my friends is working at a startup where they use image segmentation for similar purposes, where they identify the target area, and based on the segmented image, they determine the amount of dosage. Why not that? Of course, one answer would be maybe you cannot run a segmentation algorithm on a hospital computer, but any other reason?
Well, the answer is that we haven't tried it yet. It could be another path that we take with this type of research. We haven't come to this point yet, but very good idea. Thank you.
Thank you.